This is the problem we are going to solve at Parsimony. We're going to build that world model for language. When GPT reads a sentence, each word is converted into a fuzzy, high-dimensional vector. This is where we are different. This is where we fix things. We determine which discrete word and actually meant by the speaker. For instance, was it L-E-A-D, the verb, or L-E-A-D, the noun? We can use context to determine what each word resolves to. And once we have discrete words, they can do word-like things based on their surroundings, just like cars in the Tesla world model. Recently, Sam Altman, the CEO of OpenAI, was speaking at Cambridge University. A student asked, to get to AGI, can we just keep min-maxing language models, or is there another breakthrough that we haven't really found yet to get to AGI? Sam Altman said, we need another breakthrough. We can still push on large language models, like GPT. We can take the hill that we're on and keep climbing it, but within reason, I don't think that doing that will get us to AGI. So there we have it from the CEO. As great as GPT is, it won't get us to real AI. Also known as AGI, Artificial General Intelligence. We have reached a plateau. Let's take a look at why we need another breakthrough. Let's look at some words first. Think about the word discrete. It means separate, individual, like whole numbers, 1, 2, 3, 4, 5. There are no whole numbers between 2 and 3. They are separate with nothing between. That's what it means to be discrete. Next word, continuous. It means uninterrupted, like a spectrum, fuzzy, like decimals on the number line, 1.5, 8.234, or 3.14159. This distinction between discrete and continuous can be seen in an example that my hero Carl Sagan used to talk about, apple pie. He actually filmed himself cutting apple pie into half, and then half again, and half again. How many times can you do this? If you can cut something in half forever, it is continuous. But after cutting apple pie in half about 90 times, you get to individual atoms, discrete atoms. Physical matter appears to be discrete. Now, let's look at what you've learned. Are phone numbers discrete, or are they continuous? Here's how you know. Is it okay to be just a little bit off when you dial a phone number? If you're only off by 1 digit, do you almost reach the person you wanted? No. Phone numbers are discrete. Now let's consider the colors of pixels on your phone or on an image. Each pixel will have a 3-color vector, basically a list of numbers. 3 numbers, the amount of red, the amount of green, and the amount of blue. A color vector might look like 0.2, 0.3, 0.7, or the vector for pure red would be 1, 0, 0. They act like coordinates. Think X, Y, and Z. If you adjust the colors on your screen just a little, can you still recognize what you're looking at? Yes. Tiny changes make a tiny difference. That means color vectors are continuous. One more vocab word, linguistics. The study of language and its structure. For instance, we can take a sentence like, Jack gave Jill a book, and create what's called a parse tree. The verb gave sits at the root of the tree, which we ironically draw at the top. So it's more like an upside down tree. The important thing is that this tree mirrors how you think. The verb gave has 3 children, Jack the giver, Jill the recipient, and book the gift. Every sentence you've ever uttered can be made into one of these trees. As a sentence gets longer, the corresponding tree can become arbitrarily complex. Certain tree shapes are easier to understand than others. This is why some authors are easy reads while others are impenetrable. The key lesson you should take from linguistics is that the shape of the above is the shape of the thought in your head after reading that sentence. Take note, everything in this tree is discrete. Despite all the linguists have to teach us, the field of AI has largely ignored them. Just to show you how little value they give to the linguists, I want to share 2 anecdotes from San Francisco. A friend of mine was at an AI conference and happened to share an Uber with an NVIDIA employee who was about to take a new job at OpenAI. He had 4 years experience in AI ML. He was a developer, not a linguist. His new salary, 7 figures. I know that city is known for high salaries, but this guy only has 4 years of experience. Now, when I was working with an AI company in San Francisco, we needed some high quality training data, and we decided to hire PhD linguists with at least 5 years experience. We told them they couldn't work from home. They would have to physically come into our office in downtown San Francisco. We didn't even promise them a number of hours. It would change week to week. We needed to hire 5 of them, each of them PhDs with years of experience. And we paid enough to hire all 5 within 1 week. Guess how much we had to offer them? $15 an hour. That's less than Wendy's. The industry puts no value on linguistics. Why? It all started with Fred Jelinek, one of the pioneers using AI on language. Fred Jelinek had programmers and linguists working for him. He famously said, "Every time I fire a linguist, our accuracy goes up." This sentiment remains to this day. The most successful model in history, ChatGPT, is built on this philosophy. We have an algorithm that's fast on the hardware. Let's retrofit it for language. There's no need to understand how language works, no need to think about internal states. If it gets the right answer, who cares how, right? If it gets the right answer, doesn't matter why. A researcher trained an AI to distinguish wolves from huskies. It's difficult because they look so similar. The model achieved high accuracy. Job done, right? If it gets the right answer, who cares how? We believe this is wrong. Now, what they did is they used another process, which shows which part of the image were used to classify something as either a wolf or a husky. And the most influential parts of the image was the snow in the background. I think we can all agree that this model was getting the right answer for the wrong reason. We can also agree that reasons matter. The internal states do matter. What are the internal states of GPT and other LLMs? Well, it all starts with something called self-attention. It's basically a way to measure how much the model looks at connections between words. Take the sentence, "The animal didn't cross the street because it was too tired." GPT doesn't create a parse tree. What you end up with looks something like this. Are these connections discrete like a parse tree? No, they are not. They are more like color vectors. They are continuous. They are fuzzy. No two words are ever completely connected or disconnected. Everything exists in a cloudy mess of partial connections. It's self-attention matrices all the way down. At this point, it's so not like parse trees that it's almost comical. It's basically a meat grinder for words. Words input, then GPT, and words output. It's words in, words out. And what's in between? Just a bunch of numbers. If you ask an engineer why it says something, the best response is, heck if I know, it's just a bunch of numbers in there. This is known as the explainability problem. Air Canada put a chatbot on their site. A customer asked the chatbot how to get bereavement discounts, which is a cheaper flight for attending a funeral. The chatbot gave detailed instructions, and this person followed those instructions to a T. When they arrived at the airport with the details, the representative said, "No, that's not our policy." "But your chatbot said it." And he responded, "We're not responsible for what our chatbot says." Well, the court said differently. The passenger sued and won. It turns out companies are responsible for what their chatbots say, which leaves a giant conundrum. Do you take the risk and use it? Or do you let the greatest innovation of our generation pass you by for your competitors to use? Let's shift gears for a second and talk about Tesla. I consider Tesla to be one of the great AI companies. Even though it's not totally solved yet, self-driving is impressive. I like to consider what happens after a high-profile accident. Do you remember the one with the semi-trailer that fell across the highway perpendicular? A Tesla drove into it without even tapping the brakes. Why didn't it even try to slow down? Insurance companies and executives all wanted to know. It turns out that Tesla thought it was looking at a darkened underpass. Well, of course. It's not like it had ever seen the top of a trailer perpendicular across the highway before. Even though it didn't do the right thing, at least we know why it did what it did. But what if there were no why? What if, after a big accident, the insurance companies and executives asked why an accident had happened? And what if that same Tesla engineer had said, heck if I know, it's just a bunch of numbers in there? That would not fly. But somehow that's still the norm for language models. When Air Canada made its mistake, you can bet the executives called their tech staff in for an emergency meeting. Why did this happen, they probably asked. To which the engineer had to say, heck if I know, it's just a bunch of numbers in there. This is the problem we are going to solve at Parsimony. We're going to build that world model for language. Think about the Tesla world model again and what it does. You can see it while you drive down the street. The display shows what the Tesla sees. If there's a car on your left, you can see it on the display as a roughly car-shaped 3D object located on the left of your vehicle. The Tesla is constantly making predictions about where that car will go next. All of those predictions are based on a premise that this object is a discrete object, a car, and it will do car-like things. It might go forward faster or turn left or slow down. When GPT reads a sentence, each word is converted into a fuzzy high-dimensional vector. This is where we are different. This is where we fix things. We determine which discrete word and actually meant by the speaker. For instance, was it L-E-A-D, the verb, or lead, the noun. We can use context to determine what each word resolves to, and once we have discrete words, they can do word-like things based on their surroundings. Just like cars in the Tesla world model. We're bringing a world model to language.